Hi, this week we'll be discussing field extensions. We just had a refresher on vector spaces, and now we're going to talk about the special fields that are vector spaces over other fields. Okay, so first we'll define a field extension and the degree of a field extension. So, a field extension, if we say let K containing F be two fields, then K is said to be a field extension over F. Pretty straightforward idea. If K is a finite dimensional vector space, in addition to being a field, I should say over F, then the degree, which is written like this, K colon F in brackets, this is equal to the dimension over F of K, as a vector space. Okay, and we have the following theorem. Degree is multiplicative. So if we're given a chain of extensions, L containing K containing F, and we know that L, the degree of L over K and the degree of K over F are finite, then the degree of L over F is equal to the degree of L over K times the degree of K over F. Okay, and so the trick here is basically to find a basis for K over F and for L over K. So let V1 through Vm be a basis of K over F, and let W1 through Wn be a basis of L over K. Okay, then we're going to show that the products Vi times Wj for, I between 1 and m, and j between 1 and n, is a basis of L over F. Okay, and this is, and it's straightforward to see that that's equal to the product of the two dimensions of the smaller field extensions. Okay, so how do we prove that something is a basis of a vector space? Well, we have to show that it spans, and we have to show that it's linearly independent. Okay, so to show that it spans, I'm just going to get rid of this stuff. Okay, so this is relatively straightforward. We can start by taking any element in L. So let X be in L. Okay, because we have a representation of, we know that the elements W1 through Wn span L using coefficients in K, we can write X equals K1 W1 plus up to Kn Wn, where Ki is in K. Right? because we're writing this as a vector space over K. So the coefficients have to be in K. Well, the thing about K is that every element here can be written as being in the span of the VI's, because K is a vector space over F. So each Ki is equal to, let's give it F1 V1 plus up to FM Vm, where Fi is in F. Okay, great. So now we have x equals the sum of let's write it this way. It'll be a double sum where we're summing over the, how do we write this? Let's write this as, instead of F1, we'll write it Fi1, because we're going to have a lot of different ones of these. This will be Fim. This will be Fij. Okay. And now we're going to let j go from 1 to n. And we're going to m, sorry. And we're going to let I go from 1 to n. And this will be Fij Vj Wi. Okay, so we've taken an arbitrary element in L and we've written it as a sum of the elements Vi Wj, or I guess Vj Wi, since we wrote the indices backwards, and the Fij's are in F. Great. Okay, now we need to show that they're linearly independent. So let's get one more page for that. So suppose we're given some linear combination of the Vij's, and we're told that this is equal to 0. Aij Vi Wj. Okay, so that means that, so if this is equal to 0, then, well, we can group these. So we can take, so this is really a double sum. So we can group together the all of the coefficients of each Wj, let's say. So we're going to get the sum over j equals 1 to n of the sum of Aij Vi from I equals 1 to m Wj. Okay, so now this is a straightforward linear combination. So these guys we know are in, because the, sorry, this should be F, because we want to remember that these are elements of F. Okay, so because Fij is in F and Vi is in K, so this is going to be in K. So this is a, so if this is 0, this is a linear dependency over K. But we know that the Wj's are a basis, so this means that all of these summations are going to be 0. Okay, so that implies that sum of the Fij Vi for I equals 1 to m equals 0 for all j. But we know that the Vi's are also a basis, so that means that the Fij's are equal to 0 for any I and any j. And that implies that the Vi Wj are linearly independent. Okay, and that's enough to give us this relation of this multiplicative property of degrees. Okay, awesome. So a corollary of that is if we have a chain of extensions L over K over F with the degree of L over F finite, then we'll know that the degree of K over F is also finite, and the degree of K over F divides the degree of L over F. Okay, so the key here is to just observe that L over F finite, or rather, let's use the degree notation. Implies L over K finite and K over F finite. So the way you get the first one is, well, if using elements in F, I can take only a finite number of elements of L, and with coefficients in F, I can span the whole thing. Then the same is true, all the more so if I further allow elements of K. So as easy, or spanning with coefficients in K is easier than spanning with coefficients with coefficients, sorry, just want to make a new page here. In F. How about the other one? How do we know that K over F is also finite? And K over F is finite because there are fewer things to span, right? If I can catch everything in L using just a finite number of elements and then elements in F, then I can certainly catch everything in K as well. Is easier than spanning all of L. Okay, now that we have that these two degrees are finite, we can apply the theorem to get the divisibility. Awesome. Okay, now let's define an algebraic element, an algebraic extension, as well as transcendental elements. So an algebraic element, or rather, let's say it this way. An element A in the field extension K over F is algebraic if it satisfies some polynomial relation with coefficients in F. Okay. So that's an algebraic element. An extension is algebraic if all elements are algebraic. And let's make ourselves a bit of room here. Oh no. Okay. Apologies for that interlude. And we say an element is transcendental if it is not algebraic. Okay, now we can look at a concrete example that we're somewhat familiar with. Before we do that, let's first establish a basic principle here. And the theorem states that a finite extension will be algebraic. Okay, let K over F be a finite field extension of degree n, then any element A in K satisfies a polynomial of degree at most n. Which should probably be a less than or equal to here. Okay. Though, strictly speaking, it's true also for degree n. Okay, well, how is this the case? So take the set 1a, a squared, etc., a to the n. This is a set of size n plus 1. Just note this is the proof of this theorem. This is a set of size n plus 1, which means that by virtue of the dimension of the field extension, this has to have some relation, some linear relation. A non-trivial linear relation exists. And that gives it to us. Then we have implies Rn a to the n plus Rn minus 1 a to the n minus 1, etc., down to R1a plus R naught equals 0, which means that A is algebraic. A is algebraic and it satisfies polynomial of degree n. Degree n. Okay, pretty straightforward. Okay, now we can get to the example that I wanted to mention. These are considering the field of complex numbers as an extension over the rational numbers. We can look at specific elements and see whether they are algebraic or transcendental. So the first example is 1 plus I. And knowing what we know about I, we know that squaring it often helps us make it look more real, right? So if we take 1 plus I squared, that's going to be equal to 1 plus 2I minus 1, right? Because I squared is 1. I squared is minus 1. So this means this is equal to 2I. And that, in turn, if we take, what's the best way to do this? Well, if we had added 2 times itself, so if we take, or subtract 2 times itself, minus 2 times 1 plus I, so then we get minus 2 plus 2I gives us just minus 2, so we want a plus 2 after that. So that implies that this satisfies the equation x squared minus 2x plus 2. Okay? So that's one example of an algebraic number. It's algebraic over the rationals. Okay, how about this funny looking radical. So we have square root of 1 plus cube root of 2 plus square root of 3. Well, the way that we can look at this is if we call this a. So a squared minus 1 is equal to the cube root of 2 plus the square root of 3. So to simplify that expression, we can cube it on both sides. We get a squared minus 1 cubed equals 2 plus root 3. Well, then we can subtract the 2 on both sides and square it again, and we get a squared minus 1 cubed minus 2 squared equals 3, and then we can just pull the 3 to the other side, and we'll get our polynomial relationship. So this is a polynomial that this radical satisfies, and that tells us that this is algebraic over Q. As for these two numbers, e and pi, familiar from our calculus classes, these are both transcendental. So no matter how many powers of powers of e and pi you add together, or rather, you have to take them one at a time because it's not known whether e and pi are related polynomially or not. But if you take any number of powers of e with rational coefficients, you're never going to be able to add them together to get 0. And the same holds for pi. But that requires more heavy machinery to prove. Okay, let's move on with a theorem. And this is going to help us analyze finite field extensions. If D is an integral domain with 1, which is a vector space of finite dimension over a field F, then D is a field. Okay. So the key here, so if we know that D is an integral domain with 1, the only thing we really need to check is that we have division, right? We need everything that's not equal to 0 to have a multiplicative inverse. Okay, so if D is an integral domain with 1, and it's a vector space of finite dimension over field F, so we can take some, we can take any element, right? Let's take, so first of all, I'm going to say this is our proof. Take A and D. We want to show that A inverse exists, okay? So from the last thing we looked at, from the fact that, from the same argument, though it was a different theorem, we know that the set 1a, a squared, etc., a to the n will be dependent. Okay, so there's a polynomial relationship among these a's. P of a equals 0. But if we want to find A inverse, all we have to do at that point is, so we can take the lowest degree term here. So we know this is an integral domain, rather. So if we write down the equation that this satisfies, it'll look something like Pn a to the n plus up to P naught equals 0. And this can't be equal to, or rather, if this has, we know that not all of these are 0 because this has to be a non-trivial relationship for non-trivial, non-zero polynomial. Okay. So that means we have this, and we're going to claim that this is not 0. If it were 0, then every term would have a positive power of a, so you could factor it out. Pn a to the n minus 1 down to P1 times A equals 0. And then that would mean, so either one of these is 0, or this polynomial. So we have to have that one of these is 0. Otherwise, that would contradict the fact that we're in an integral domain. Again, we've got to specify that this is not equal to 0 because we're never going to invert 0. OK. So we have that P0 is not 0. Okay, so that means that Pn a to the n plus down to P1a is equal to minus P0, where this is not 0. Okay, so since it's not 0, and we know that all of these pi's are coefficients from the field, so this is going to be invertible. So we can multiply by the inverse of negative P0. And we get negative P0 inverse Pn a to the n plus, etc., negative P0 inverse P1 a equals 1. And now we can factor out our a, and we get negative P0 inverse Pn a to the n minus 1 plus down to negative P0 inverse P1 times a equals 1, which means a has an inverse. A inverse exists. Okay, so that means that because we started with an arbitrary element in the integral domain, we were able to invert every element in the integral domain, which means it's a field. So let's go into some more detail about the polynomial relationships that these elements of a field extension satisfy. So our first definition is algebraic of degree n. So we say that let A be an element of a field extension. We say A is algebraic of degree n if the polynomial of minimal degree let's call that P of x, of minimal degree satisfying P of a equals 0 has degree n. Okay. And the minimal polynomial is exactly that P of x. Okay. So we can state a lemma that the minimal polynomial of an element of a field extension is irreducible. Okay, so if A is our element with minimal polynomial with P of x is irreducible. Okay, well, if you could factor P of x equals, let's call it f of x, g of x, where both of these guys are in f adjoin x, then P of a equals f of a g of a, but that has to be equal to 0 because that's the polynomial relationship that P of a satisfies. But f of a and g of a, if this is a true factorization, will have smaller degree than P. And P of x. Let's call these f of x and g of x. If either is 0, it contradicts minimality of P, but if neither is 0, it contradicts that it's an integral domain. Okay, so with that contradiction, we prove that the polynomial must be irreducible. Okay. And this leads us to the main result of the section, which is that the polynomial ring of f using a, so polynomial expressions with a, gives us a field extension over f. So if a and k is the algebraic of degree n over f, then f adjoint a is the smallest subfield of k containing f and a, and is finite over f of degree n. Okay, so the first thing to prove is f adjoint a is a field. Okay, and this, well, we know that this is an integral domain. Okay, so so it's an integral domain. Since it's contained in a field, it doesn't have any zero divisors. Okay, and we also know that it's finite dimensional as a vector space over f. Since it's spanned by one through a to the n minus 1. Okay, and for any higher powers, you can use the minimal polynomial of a to deduce relationships you can do polynomial long division, use the Euclidean algorithm to get a multiple of your minimal polynomial plus something in this span. Okay, and since the multiple of the minimal polynomial reduces to 0, you're just left with something in this span. So that means it's finite dimensional, but as we just saw, a finite dimensional integral domain is a field. This implies FA is a field, and that's why we give it the honorary parentheses marks. Okay, you'll recall this is the way we denote fields of fractions, fields of fractions. And it's finite over f of degree n by the argument we just made. So for that reason, we have this finite extension f adjoint a living in K. Okay, but another way to think about this, instead of starting with an element of A and then starting with an element of your field extension, and then attaching it to the subfield and determining the degree of that. Another way to think about this is to start with your field f. Okay, so we want to take f adjoin x, okay, the polynomial ring, and then we want to map that with a map C or psi to K, okay, to this larger field. Okay, and we're going to take an element f of x here, and we're going to map it to f of a here. Okay, so now you want to consider what is the kernel of this map. So the kernel of psi, this is the ideal generated by the minimal polynomial of a. Okay, and we know that the minimal polynomial of a is irreducible, so this is a maximal ideal in the polynomial ring with one variable. Okay, and we know that when you take a ring and you quotient out by a maximal ideal, you get a field. Okay, as for the image of this, well, what's the image of f adjoin x into k if we're just mapping to polynomials of a? Well, that's going to be precisely f adjoin a, or what we've identified as fa. And so another way of putting all of this is that using the first homomorphism theorem, or isomorphism theorem, we've really defined this field as being f adjoin x modulo the minimal polynomial of a, and that's isomorphic to f adjoin a. Okay, so that's another way of looking at the same thing, and it'll give us ways to construct field extensions going forward. Thanks so much.